I'm Jake Kennard. I work at the University of Bristol. I should say thanks to the organisers for inviting me. So this talk is going to be about integrated QKD. I should say that this chip is not QKD, it's just a nice picture. I like it. It's a, Josh Silverstone took this, he may be around at some point today. I don't know, you can ask him what it is. So I want to talk about two experiments really, both about integrating QKD into chip-based platforms. The first one is a little bit older, so I will kind of whip through it, and then I'll really talk mostly about some recent work in silicon. So why do we want to do QKD in chips? Well, the main reason is actually, if we ever want to get QKD into the real world, we kind of imagine that the way that it's done at the moment, commercially at the very least, in these kind of big boxes with big spools of fibre, is not maybe the best possible way of doing things because it's not particularly scalable. And if I ever want to get it in my phone or my computer, it's probably going to look like a chip and probably not going to look like one of these. So that's kind of one of the main kind of reasons that we're kind of looking at doing this. Of course, there are other benefits as well due to the low weight, certainly low power usage, stability, all the rest. So this is some work done primarily by Phil Simpson, who's sat at the back, a little while ago now, basically doing QKD from one chip to another chip. So the top chip here, which you almost certainly can't see the laser, is made of indium phosphide. This has all of the optical components you need to essentially create QKD pulses. So it has an integrated laser here on the chip, and then essentially we can, through a network of essentially Mach-Zehnder interferometers, create a whole bunch of different pulses, and I'll talk a bit more about those in a second, and phase shifts such that on the output here, we have our weak coherent pulses of some intensity, which we can use for QKD. And this type of thing will clock at around a gigahertz. It's supposed to work around 10 gigahertz, it didn't quite work around that. On the other end here, we have a different device that's made of silicon oxynitride. This is a more low-loss device. So in the top device, if I lose photons in the device, I don't care because I can just turn up my laser. Of course, when I get to my receiver, I certainly want to keep all the possible photons I can get, because otherwise I'm going to lose key. And so you can kind of see that actually this really is just an asymmetric Mach-Zehnder, which has a digital tunable delay with a bit of balancing for loss, and then also a second arm here, which we kind of use ultimately to do time bin measurement in some respects. So this is the chip, so we like showing pictures of chips because they look cool. So this is the indium phosphide chip. You can sort of see it's about 6 millimeters long, and this one's a little bit bigger, and that's mainly due to the fact that typically if you want lower loss devices, you would tend to be less confined. So this slide is a little bit busy, but this is essentially to say that we can use these devices to do 3 different protocols by just reconfiguring the device. So this is essentially BB84 encoded in time. So we essentially take our pulses, our CW light from our laser, and essentially carve out pulses using this pulse modulation Mach-Zehnder interferometer. There are some numbers here if you kind of care about these things, but the pulses tend to be on the order of 150 picoseconds wide-ish, and they tend to be split by about 550 picoseconds in general. But although that's somewhat tunable, that really is actually set by these delays here for the re-interference. So for those of you in the know, we've done sort of BB84, differential phase shift, and they're very similar, and also this coherent one-way protocol. So this is all done just by rearranging the phase shifters, etc. So I don't want to go on about that too much. What I really want to talk about is silicon. So silicon, you might immediately, if you know anything about silicon photonics, you might immediately think this is a terrible idea because there is no easy way to do lasers in silicon, and also phase shifters is kind of hard to do in silicon, certainly fast. However, sort of almost everything else about it is kind of good. So pretty much you've got some really, really tightly confined waveguides. You can do really nice coupling on and off the chip, really nice Morse-mode couplers. Potentially even delays are potentially quite nice. There's certainly been some recently which have been very nice. Potentially even detectors on the device. So it's a very nice platform which is particularly mature, and particularly if in the future people can integrate electronics alongside. It's very appealing. So I'm not going to talk about how to do the light generation on the chip. I'm going to talk really today about the phase shifters. So the phase shifters that people tend to use, this is a cross-section of the waveguides, really tend to be these thermal optic phase shifters. So these are essentially using thermal optic effect to essentially heat across the waveguide, and this induces a phase shift. So these kind of work at kilohertz speeds, but they're very, very nice. They're very kind of, you get very good extinction. Certainly if you put in a Mach Zehnder, you can get about 30 dBs worth of extinction. And you can easily do kind of full 2 pi worth of phase very easily, just by increasing the voltage. And the phase goes with sort of quadratic-ish in voltage. And that, I guess, is this sort of plot here. And you can kind of see you get these nice deep dips. However, they're slow, because of course it depends on the change in temperature. However, if you make one of these devices, which is essentially a carrier depletion modulator, by doping the device, this is essentially a P and an N, it's basically a PN junction, you can cause a phase shift essentially by controlling the density of free carriers within the device. So obviously, if I have some free carriers in my device, if the light comes in, it essentially can be absorbed by those and re-emitted. As you know, obviously that will cause essentially an effective change in the index. So by controlling the amount of free carriers in there, I can control the index and therefore induce a phase shift. However, I'm doing this by controlling absorption. So this is essentially going to essentially change my transmission as a function of voltage, as a function of phase. So that is really kind of a pain, because it's going to cause some errors based on phase. We do this in a way where we actually sweep out the carriers, so we kind of deplete them. And that is essentially because if you add more carriers, you add more loss. So we kind of want to work in this kind of least lossy region. And also it's quite efficient to build them like this with no intrinsic region, which actually means we can go really fast, which is the key advantage. It's pretty much the only advantage. And so these are the kind of the plots that you'll see that actually the extinction is not so good, and we actually end up saturating, really, our phase shift. And that's kind of obvious, because at some point I'm going to sweep out all the carriers, and then there's going to be none left to sweep out from those. So how do I use this to build QKD? So this picture essentially is in Parthia Coding, which we had kindly introduced to us earlier. So this is the math for those who like the maths. However, I'm going to draw a picture, because I like pictures and I think it's kind of easier to see. We set up this interferometer to essentially, by default, have our light coming out in the plus I state. And then we can essentially switch each of these carrier depletion modulators on in turn to choose the states we want. So if I hit this one here, it essentially rotates up here. I can do that by pi by 2. Similarly, if I go to do the bottom one, I go down to the bottom. And then, okay, on the outside here, I can add phases in the same way. And in that way, I can get essentially all of my 4 states that I need for QKD by just really operating in the regime where I go from 0 to pi by 2. So I don't really need to do very much phase shift. The other subtle thing here is that actually, because the transmission is changing, I'm actually essentially creating a bit of a mixture as I go along. Because as I turn on one of these guys, the probability that a photon goes through the bottom one is higher. So I actually cause a change in my state. So it's actually kind of like making a rotation here. So this is kind of exaggerated for effect. But you know, these lines are now smaller, they're kind of mixed. But what you do see is they're still orthogonal. And that's really kind of the key point, that actually we can still get good basis discrimination. And if you kind of do the maths, turns out that you know our state prep is about 99.5%. This is theoretical. Which corresponds to a Q bar of about 1.1, and that really mostly comes from this. So, how do we actually use this? Because of course, clearly Parthia coding is not the greatest way to do QKD over any channel. Well, the way we do this is essentially convert it to a different encoding. So in this one, we essentially convert to time bin encoding, so we convert from path to time. The way we do that is by adding a small delay in one of the paths, and then recombining on a beam splitter to join the paths together with a 50% loss, and we just ditch this output. And because again we're using weak coherent pulses, we can just turn up the laser by half, or by double lines. These are kind of the states that we get, and actually we use the same chip as the receiver to decode. However, having said that, the silicon, for anyone who's worked with silicon, you know that losses are large, and actually. Getting serious amounts of light out of this was incredibly challenging. You could see that actually the state preparation is pretty good, and we could build up statistics pretty reasonably well of the receiver for those of you who are kind of familiar with this type of thing. However, the stability was not very good, particularly because of the long time delay. Actually, if you do the maths, you end up seeing that this is mainly due to temperature stability. Because the delay is long, you need much more stable temperature control than we actually had. So we anticipate that actually, okay, with lower loss components, okay, this would work, but actually more critically, if we were able to reduce this delay, we would have a much better chance of actually interfering in these pulses more successfully. So the other way of doing this is essentially converting to a kind of maybe a more traditional way of doing it, which is polarization. So the way that we actually did this is with a device called a Parthia polarization coupler. Essentially what this is a grating coupler. So the light comes out vertically, but it's sort of two on top of each other, sort of crossed over. And so if the light comes out of one of the waveguides, it's going to emit vertically-ish in one polarization, and if it's in the other, it's going to emit vertically-ish in the other. And so, of course, I can have a coherent superposition of those, and so I can convert efficiently from path to polarization, and back, of course. So for this guy, learning the lessons of the loss in silicon, we actually use just a fiber receiver, which is just built like this. And this is just to say that actually, this is the kind of predicted state preparation that we imagined we would get out here, and this is actually what we measured. It's pretty close. And you can see that actually we were able to do QKD. Okay, this is clocked at about 1 gigahertz. So this sort of shows that we can kind of reasonably clock these at some fast speed, which is kind of the whole point. And actually, you won't remember this, but I certainly do. This 1.1% was what we predicted at the start in terms of our Q-bear. So we've not actually necessarily added more errors by actually doing this physically. We've actually, I guess, modeled it well. And the other thing is that this secret key rate might seem a little low for those who are familiar. Actually, this is not using decoy state, which is completely compatible. We just didn't have that in the chip. So we imagine that would go out further with the addition of that. And that's a picture of a chip, because I said I like pictures of chips. So yeah, actually, obviously you can see this is much smaller again. Actually, this has both the time bin and the polarization on it, so it's significantly smaller. So the other sort of final thing that I want to get through, because I suspect I'm getting near the end of my time, is that actually I can use these devices to modulate pulses in and of themselves. So previously I was sending in pulses of light and using the waveguides to essentially encode them. I can actually use these devices to create pulses, which is actually a potentially valuable thing to do, particularly given how we worked in the Indian falsifier. The way that you might think about doing this is essentially by tuning your phase, your static phase, which is your heater phase, such that you maximize this extinction. And if you think about it, that will be exactly this point where you essentially hit on a pi phase shift. And so this is exactly what you can get, and actually you can get a pretty good transmission, extinction of about 25-ish dB, which is actually kind of encouraging that actually these things are kind of a bit more general than as we kind of imagined. And this is, I guess, some images of these suitable for QKD. And the natural thing to do for that is to actually use this just to do coherent one way, if you're familiar with it. So these are, again, the kind of states that we're interested in, whereby the 0 is sort of in some way encoded before in time and the 1 after time, and then you sort of have this sort of decoy type thing checked for, which you ultimately use to really check for eavesdroppers. So this is sort of really just like a switch. But actually it's kind of a nice switch. It's a very stable switch, it's a very high extinction switch. And actually, again, we were able to use that and get out pretty good results. This receiver is actually the same receiver we used for the other chip-to-chip experiment. So goes to show, I suppose, that it has more than one use. You can use them again, which is always good. And again, Q-bears are pretty similar, and we pretty much found that this was pretty reasonable pulse length. We were reasonably limited by that, about 175 picoseconds. And again, being able to clock quickly was the main issue for us. So that was my whistle-stop tour of silicon QKD. Again, I told you I like pictures. There they are. Thank you very much.
Why was stability such a big issue?
Well, it's because of the essentially the asymmetry of the maximum. So the delay was something like half a nanosecond, and in essence, if you kind of look at the fluctuations over that period, over that sort of time period, and match that up against essentially the phase difference that you would get, then essentially that's where.
That's what I'm asking for. What was the temperature fluctuations?
Oh, it's like 0.01 degrees we had, but we need 0.005.
And what was the time scale for that?
I didn't measure but this is over over a certain amount of time. I guess the statistics of it. But that was just off the bat. It was not slow enough that we were able to track it. We sort of.
Thank you for your talk, Jade. Just thinking about the stability, did you need to run some sort of a clock to stabilize it, and how long can the experiment run?
Yeah, so for all of them, pretty much, we essentially synchronize our. So this is, I guess, this synchronization. So So we essentially, depending on how we do it, how we choose to do it, we can use, for example, the output of this as a clock. We can also use an alternate laser, because ultimately our syncs come from some classical electronics. And then essentially you have a photodiode on the other end, which then goes into our counting electronics.
So how long can you do this? It's like a burst mode?
No. I mean, this is stable over length of experiment, I guess, which is a day potentially for as long as. I have no idea how long it can go because I haven't tested for weeks. So, but it seems pretty stable so far. But it's not a sort of self-optimizing system. And clearly, if it drifts off, then it will essentially just.
Any other questions? One that's time to.